So why do you have to be careful? In order to see that, just let's have a look at the momentum equations only including bottom friction. Okay, simplified problem. So we look at these equations. You only have bottom friction included. On the right hand side is the force. This is the bottom friction force. It's modulated through specifying a value for R. If you set R to 0, no friction, and if you use a value here, your positive value for R. Okay, and it's negative because it's always opposite to the direction of the. So what happens? This one is an initial value problem. So you specify some initial velocity at the beginning. Okay? And then all that can happen is that the velocity becomes weaker and weaker and disappears. Yeah? So you can even make it easier. Okay, make it easier and just look at only one dimension. So this is, then you can formulate it as an explicit scheme. Explicit scheme means this: you have the old velocity component u here. This is only the u component. Then if you include the friction term, you have a 1 minus epsilon, and the epsilon you can relate to the friction parameter. Yeah. And with this one, get a new value, n plus 1. So it's an iteration. You can repeat and repeat and repeat. Right? All right. And then you have to be a little bit, not careful here, but you have to work out that I use the writing HU here because the H value has to be interpolated on the U velocity. So this is how the grid looks like in one dimension. You predict at U, okay, and the water depth or sea level points are to the left and to the right, and you actually have to take the sum and divide by 2, and then you have it interpolated on. So this is what, just a little detail. So, but now what's the problem? Okay, the problem is, what could happen is that this epsilon exceeds 1, and if this one is larger than 1, all of a sudden 1 minus something larger than 1 reverses the sign. Okay, so instead of actually the friction always reducing the speed, all of a sudden you get a positive acceleration. Okay, so you get something that, and a reversal of the direction all of a sudden, which is absolutely nonsense. So in terms of numerical stability, you have a condition. Epsilon has to stay less than 1. Also 1 doesn't work. 1 just means all of a sudden no flow anymore. Imagine you have 1 with this equation. 1 minus 1 is 0. And the new predicted velocity turns 0. And then there's no more change after. Absolutely rubbish, isn't it? So you have a stability condition. However, you can altogether avoid this problem. And you can avoid it through the use of a semi-implicit scheme. And this is how it looks like, semi-implicit. Okay, so let's start again. You have this simplified problem. It's only bottom friction included here, just to focus on the key points. And you can write a semi-implicit scheme. And semi-implicit scheme is just a mathematical trick. No physics behind that. What it means, a semi, is that one part, you use the existing information at time level n, which is here on the left-hand side, here. And at some part, you use actually information from the unknown next time level. Yeah, un plus 1. You see this? Vn plus 1. It's only a trick. And from using this approach, you now bring everything that you don't know onto one side of the equation, everything you know onto the other side, and you get what's here in this red box. This is how the approach looks like. So you have an current velocity components, and then the prediction takes this and divides by 1 plus positive number, and it always, if you work it out, you plug in some values, you always can only reduce the number, your velocity magnitude. No matter how big r is always a positive number. You can look how it's formulated. Why is it always a positive? Have a look. R is a positive parameter, delta t times f is positive. These ones here are squares. Okay, this is the velocity component squared is positive. Water depth is always a positive quantity. So it's always stable. So here there can be no weird things happening if you use the semi-implicit scheme. And this is a very, very important trick, and that you can also use if you have more than bottom friction, if you have other terms. So this is one of the special secret tricks in oceanography, using semi-implicit treatment of bottom friction. Yep.